Alright guys, welcome back. Today we're going to talk about DNS servers. Uh, the discussion really about DNS servers is a lot wider than what we're going to cover today. Obviously, since this video is focused on the RHCE exam, we will concentrate only on what's relevant to the exam objectives. But still, we will cover some theory. So on this video, we're going to start by talking about the toolbox as usual, just to make sure you guys have all the tools that you need to complete all the tasks that we're going to discuss today. And then we will talk about the domain naming system. What does it look like? How and how it's architected, right? A bit of the architecture of the DNS or the domain name service. Then we will talk about DNS lookups. Understanding how DNS lookups work is very important for your exam objective. So we will cover it and we discuss DNS lookups and how they go, right? So and this is going to be very important for your to understand how to configure a caching naming server. Then we will talk about DNS results records, just to give you a good idea of what kind of data comes back from a DNS server and what kind of data we can look for when we're looking at when we're doing a query against a DNS server. And after that, we will start talking about what's the configuration that's relevant to the exam objective, which is a caching name server. So we will discuss what a caching name server is, and then we will discuss how to configure it. And I'm going to give you a couple of tools that you can use later on as well to do some configuration verification and to test that your server is working. And as usual, we will close with a proposed lab, right? Something that you can take away for you and then you can go back to your environment and start playing with it. Right, so your toolbox, I included two links. These two links are part of the IETF, and then the first one is the domain name concepts and facilities, which is the RFC 1034. This is the RFC standard 1034. The second link will be the domain name implementation and specifications. Right? These two links, if you feel that when you're done with this video, you still want to learn a little bit more about DNS, that's a good place to start. Although there's a lot of information on the internet about DNS and how it's architected and all that, but these are what the standards are defined in case you want to take a look. So I always recommend to go straight to the standards. The second important tool that you would need is the ITSI unbound.conf. The reason why this is an important tool is because that file has a lot of the help that you would need to configure your unbound server. And we take a look at it and you will see how we can use it. Obviously, there are the two tools that we can use to check the configuration for unbound and also to play with the cache of the server. And for those two, we have a main page for each of them, which is the main unbound-control, and then the main unbound-checkconf. So we'll go through those two main pages as well, in case you want to use it to troubleshoot a little bit, and if you want to take a look at the cache of the server and understand what's going on and if the records are there or not. Right? Okay, so the domain naming system is a hierarchical naming system. It's typically used to find network hosts. If you think about it, right, the internet is a very vast, very vast web of hosts, and it's very unlikely that you will learn all the IP addresses there, particularly now with IP version 6 in the picture. So think about it. If you want to go to google.com, if the DNS, the domain name system didn't exist, then you wouldn't be able to just go to your browser and type www.google.com. You would have to know one of the servers hosting the google.com site. And you will have to know at least one of the IP addresses to enter there, memorize it and all that. So It's really not practical, right, in such a large network. And for that reason, the domain naming system was implemented to be able to provide a hierarchical system that would allow users or clients to use a host name and then get the required IP address, and also for clients to have an IP address and get the host name associated with that IP address as well. In cases where you want to use, the host name to do access control and stuff like that. Just to give you an example, also in which case you might have an IP address and you want to know the name. Let's say that you're using NFS and you are going to restrict access to your NFS server to maybe the domain example.com. If a host named server1.example.com tries to access your server would receive a request in the form of an IP address, and it will have to go back to your DNS server and ask for the name associated with that IP address to make sure they can, the server can make a decision if this host is allowed to use that resource or not. So the architecture of the DNS server is it uses domains and domain namespaces, and then on the domain and the domain namespace, then it uses subdomains. If you look at I have a small picture on the left that shows, the way it would typically look a hierarchical. The group of domains, right? So let's go and take a look at it. On the left side here, we have the ARPA, and then under that domain ARPA, you have INADDR and then .IP6. This particular domain is actually the one used to do reverse lookups. So this is for when you have an IP address and you want to find the host name associated with that IP address. So on the left side here, you have INADDR, which is for IP version 4, and then .IP6 for IP version 6. Now, the rest here are really for in the cases where you have a host name, and then you want to find the IP address for that particular host name. And normally the host name is found all the way at the end, and you will see something very familiar here, right? So let's say on the right-hand side here, we're talking about we go from the bottom up, right? So we have www, which would be your host name, right? Or FTP or records, right? This is your host name, and it belongs to the TXDPS subdomain, right? And the TXDPS subdomain is a subdomain of the .state subdomain, and then the .state subdomain is a subdomain of TX, and then a subdomain of US, and then a subdomain of root, right? So if you go from the top down, then for example the US is a domain, and then the tx.us is another domain, the state.text.us is another domain, and then the .state.text is another domain, right? Obviously, state is a subdomain of the TX, dot is a subdomain of state, and TPW as well, and then text.dps. Well, you get the idea here, right? The .state subdomain has a www host. So this is how domains and subdomains are arranged, right? When we talk about a domain namespace, it's actually the boundary that belongs to that domain. So if you talk about the txdps.state.tx.us domain namespace, that domain namespace includes everything that's underneath it. So the www, the FTP, and the records, right? If we talk about the tx.us domain namespace, it obviously includes the state, the rest of the subdomains, and all the hosts underneath it. So that's actually the boundary of that particular domain. And the domain namespace for the root, which is the dots, obviously is everything. So it would be the whole internet. And now We're going to talk about queries, but just to give you an idea why the hierarchical way to arrange all this name is because then you can actually have a set of queries just to find the host that you want to find. And let's say that you want to find this host down here, which is www. It's really far down, but someone on the other side of the world is trying to access www.txdps.state.tx.us. What that server has to do, it has to send a DNS request to its DNS server, and the DNS server, depending on how it's configured, it can start from the roots and then ask, I'm looking for the .us, and the root would say the .us is on this particular server, and it's going to send information about the server that owns the .us domain. And then that server can come back and query that server that owns the .us domain and ask for the TX domain. And it will obviously return with the information required to find who owns the TX domain, and so far and so on, right? So the server that owns the .tx domain will send information about the .state. The .state will send information about the TX DPS, and the TX DPS is going to return with the information about all the data requested, which might have been either, it might be a record trying to figure out what's the IPv4 or the IPv6 address of this host name. So that's why it's built this way, just to make sure that you have a way to find any domain at any given time. So every time you register a domain, you are probably going to be on one of those top level domains, right? These are known as the top level domain, which is the ARPA is obviously reserved for IP addresses, but then you have the .com, .net, .org, .gov, .us, .uk, and then obviously they are others, right? But these are known as TLDs or top level domains, right? In the case of US and UK, these are also top level domains, but these are country codes. Some countries they have their own country code, like for the United States, US, for the UK is UK, the United Kingdom is UK. Okay, so how DNS lookups work? In the case of Red Hat Enterprise Server, and I would say pretty confident that most Linux systems, once you configure your DNS server, that information is stored on the etc./resolve.conf file. And that file will have information about who your DNS server is. And then once your client knows who your DNS server is, it can send DNS requests to that server. And that server is going to, depending on the DNS request, is going to deal with the request. It can deal with the request with different ways. The first way to deal with the request is using a local authoritative. I mean, if it has local authoritative data, and let's talk about this kind of data here. The local authoritative data is when the server that received the query for a host name owns the zone for that DNS request, right? So it's the way it says here, when a server receives a query for host name, it will check first if the query resides in a zone that is authoritative for it. If so, the server will respond with the client with the DNS information. So let's say that you're talking about that you're trying to access a resource that's in your local network, for example. And this is very typical. When you have your own local network, you have your own DNS infrastructure, and then your own DNS infrastructure is probably going to have information about all your local hosts, right? So most probably when you query your local DNS server, it will be authoritative for that DNS zone, and it can return the data right away without having to go into a recursive query. And the way to see if the server is authoritative for that data is because when the data is returned, it returns with an AA flag, which stands for authoritative answer. So it will give you an authoritative answer, and it would reflect that on the header of the response. But obviously that's not always the case, and you might have a local cache non-authoritative data. Meaning this is data that your DNS server has in cache because it accessed that data previously. So let's say that you have a network with 50,000 clients, and I would say that the www.google.com is a very popular page in your network. Obviously, when you query your DNS server for www.google.com, what the server is going to do is going to keep that information in cache. So it's going to go out, figure out what's the IP address for host www.google.com, and then it will keep it in cache. So all the clients, when additional clients come to request for the same information, it has it already there and doesn't have to go out and keep all that kind of traffic on the network. DNS traffic can be relatively, it could get big if you have too many DNS requests going out. Obviously, since the internet is changing all the time, the data will be stored in cache only for as long as the data is valid, which means until the time to live of that data expires. And and obviously you do have a remote non-authoritative data or recursive queries, which is when the DNS is not authoritative of that data, and then it has to go out and then find information on behalf of the client, right? And then obviously that's what happens most of the time. I would say initially, if you're looking for an unknown, a site that is unknown to the DNS server, the server is going to start going through that process that we discussed right here, which is a recursive query. It's going to go to the root hits, and then it's going to go to top level domains, and and then from the top level domain, it's going to follow that tree until it finds the hostname that you're looking for. Okay, so these are regarding DNS lookups. Obviously, the data that's going to come back for you will have certain fields, and those fields are used just to identify and for the DNS service to know how to treat that data. So, so the first important field is the owner name, which is the name for the resource record, really, and this is basically what really you're asking for, right? The second is the TTL, or is the time to live of the resource record. As we discussed earlier, this value is going to tell the server for how long that data is valid. So it will tell the server not to keep that data in cache for longer than the TTL value. The third field is the class of the record, which is almost always IN for internet. And then the fourth field is the type. This is the sort of information stored. For example, an A record for a host with an IPv4 address, or a AAA or an AAA record for IPv6 address, or an MX record when you're looking for DNS data and whatnot. And then data, which is basically the data stored in the record. And at this point, I wanted to just go back to the server and do a quick demo on what this how this looks like. So I'm gonna use the tool dig, and this is a very useful tool for you to figure out, to get a lot of information about DNS. So the first thing I'm gonna do is gonna be dig on www.google.com, and let's see what comes back. And as you can see, we return the hostname www is an A record, right? And it's giving me the IP address for that host. Right? This is what came back from that reply. So let's look at this reply real quick, because this is important for you to understand when you're doing troubleshooting. So initially, he is just going to give you some information about the status of the query. If you look at what's important here, is the status. It says no error, right? And then obviously this is the ID of the reply that you received. But this is important. If the query was successful, it would say here there was no error in the query. And then you have some of the flags here. The interesting flag really is this one here, which is RA, which it tells you that it's a recursive answer, meaning the server that responded, the server that you query for this information, which is let me show you to see, which is the name server a.a.a.a, right? This server is not authoritative for that, for the www.google.com, right? And actually, if we wanna figure out what server is authoritative for the www.google.com, what we have to do is ask for the SOA record, and that will return, as you see here, you have a different flag which shows authority 1, which is telling you, the number of authority servers that is returning. And for the google.com domain, it's showing as ns1.google.com. And this is the server that has the google.com zone in it. So if we want to look at the error record for www.google.com from that particular server, we can do add ns1.google.com, and then let's ask for an error record, and then you can see that the flag changes to authoritative answer, meaning that server that we just queried is authoritative for the google.com domain, and therefore it didn't have to go anywhere. We just asked the server, and the server returned the information that right away, right? And he's authoritative for it. And you can experiment with your dig command. Also, another important one is the MX records, and I'm going to ask for MX records for google.com. I know that google.com is a domain that's used for emails, and then it returns all the MX records for google.com. And if we have any CNAMEs, that I guess you can also ask for CNAMEs for it, right? So okay, so that's that's what the data that comes back from the server typically looks like. And it's important to understand that data to have a good grasp on the actually on the type of information that's coming back. And here in this document, I listed some of the most important ones. As you can see, it's a long list, right? But let's talk about the most critical ones. I'm going to ignore the ones that they are not typically used too much. But the information is here if you want to download this document and then go through it, right? So the first one, and I would say the most popular one, is the ED record, or the address mapping record. And this is used for IPv4 addresses. So this record, when requested, it returns only the IPv4 address of the server, which is what we did initially here. And let me just clean this up a bit. If we ask for A, we return that IPv4 address, right? As you can see there, right here. The next important record is the AAAA record, right, which is the IP version 6 address record. It's also known as the Quad A record, which is basically used for the same reason, to specify an IPv6 address of a host name. And we can request it adding AAA, and obviously we'll return the IPv6 address for that host. The next one that's very important is also the mail exchange record. So normally, when you're sending an email address, you want to not just know a host name. You want to really know, for that particular domain, what are the servers that are ready to receive emails for that domain. And that is this is what is called as a mail exchange record. And obviously, as I showed you earlier, for Google, if we do an MX for google.com, what returns are these 1, 2, 3, 4, 5 servers, and your mail server at this point can sit down and then pick one of them based on the weight of the priority of the mail server, and send it to that particular server, and the server will be able to send the email to the right mailbox. If we move, I'm ignoring the host information record. There's some information here on what it is. It's basically a standard value, and then the integrated service digital network record as well, right? If we go next, then we have another important record, which is the name server record. Name server record is it specifies the authoritative name server for a given host, right? And let's just do that. So the host is www.google.com, and then I want the NS records, and then it returns, the name server that's authoritative for that server, meaning that's the server that we can go in and actually, update that particular record because he owns it, and obviously the response is going to be, faster from that server. So the second one is the pointer. The pointer record is, as we said it initially, and let me just go back on the slide a bit. The pointer is used for this particular domain here, which is the ARP and then the IN address and the IPv6 address. The pointer is really used for to take a host name and then convert it into an IP address, right? So it's actually the opposite of the A record or the quad A record. And the next important one is the start of authority record. This record specifies core information about the DNS zone, including the primary name servers and the email of the domain administrator and then the serial number of the domain and some several timers related to the refresh of the zone and stuff like that. And the DNS system also includes a TXT record or a text record, which is just a record where you can add any arbitrary text strings. Okay, so moving on, let's talk about what's important for the objective of the exam. The RHCE objective requires for you to be able to configure a caching name server. So a caching name server is really a server that performs queries on behalf of the clients and then stores the data on the cache until the TTL expires. But it also does a DNSSEC validation for your server, which means the server would be able to validate the authenticity of the DNS data that actually came back. Think about it. If you look at the internet, DNS servers are the target of many flavors of attacks on host and on all the networks, because particularly you can trick a client into believing that the DNS data that's returning is actually valid. And you can do that by poisoning your caching name server. If you poison the cache in your caching name server, then every client in your network would receive the wrong data, and then if you're trying to access, let's say that you're trying to access your Hotmail address, an intruder could poison the cache of the name server with the wrong data and redirect the Hotmail queries to its own server, and he could have a replica of Hotmail, and then potentially getting all the usernames and passwords for all your clients in your network to access Hotmail. This is just an example, right? A way to avoid that is by using DNSSEC validation, because DNSSEC validation is going to make sure that the authenticity first, meaning the response comes from a valid DNS server, and then also the integrity of the data, meaning that the data actually left the server and then it got to your server and was not altered on the way, through the internet. Right? Okay, so now we are at a point where we can do a demo on how to install and configure a caching name server. The tool that we use to install to configure your caching name server in Red Hat is Unbound. Although there are other flavors of DNS servers, I think that Bind was a very popular one. But Unbound is the one that we're going to use today. I included the steps here on what do we need to do and what are we going to do right now to install and configure Unbound. First we install it, then we start and enable the service, and then we add a firewall rule, and then we have to configure the network interfaces to listen on. Meaning these are the network interfaces that you will use to, for the server to listen for DNS queries. And then we're going to configure some client access control, and then configure forwarding. And this is one of the characteristics of the caching name server. The caching name server, what it's going to do is it's not going to do a recursive query, meaning it's not going to go to the root heads and start trying to figure out the name of the server. What it's going to do is going to just send that information to a specific DNS server, forward it to the server, and then the server is going to start recursing on behalf of your server, and then just return the data, right, when it finds it. So for that, we configure forwarded, which is basically an upstream DNS server. Right? In our case, we're going to use 8.8.8.8. So we will tell this server, whenever you receive a DNS query, just send it to 8.8.8.8, and then that server will take care of finding the answer to the DNS question. We're also going to learn how to bypass DNSSEC validation for unsigned zones, right? Because although verifying the authenticity and integrity of DNS resource records is very important, you might find DNS zones that are not signed because the owner of that DNS zone hasn't implemented DNSSEC, and this could happen, particularly for internal domains. So in the case that you need it, I'm going to show you, how to bypass that DNSSEC validation for a particular domain. And then we're going to talk about a couple of interesting tools. We already saw Dig, how to use it, and then we're going to talk about unbound-control and then unbound-checkconf. Okay, so first thing that we need to do is install unbound. So yum install. Okay, and as the server gets installed, normally the order of the steps, you can actually use them at your own discretion, but I would strongly recommend one thing specifically. And in the case of Unbound, when you start the service for the first time, it creates some of the files that you will need later on. So basically, right now, if you try to if the server hasn't started for the first time and you try to configure it, you might have some odd behavior. So, for example, let me just show you quick. Unbound. You see, if I do unbound-checkconf, what this tool does, it just checks the configuration, the unbound configuration, and make sure it's correct. So we just installed the server. So as you can see, it's failing the check, right? Because it's missing some keys and some stuff, that still don't exist because the server hasn't started for the first time. So, I would strongly recommend that first you start the service and obviously enable it, right? Right, if you do the check config now, then you will find that there are no errors on the unbound configuration file. All right, so the next step, is always, to include a firewall rule. And then we do that using the firewall CMD. We add service DNS. And then obviously we add it to the permanent configuration. That way, our file is going to allow for DNS queries to reach the server. Right? So clients, can actually use the service as a DNS server. So now we have the service started, and we have already we have the service enabled, and then we have the firewall rules ready. So the next step is to configure the server, and for that we have to configure. We're going to use the configuration file. So as I was saying earlier, there's really no need for a lot of help when you configure unbound. The unbound config file has a lot of information in there. So if you, let me just cat etc unbound and then unbound.conf, right? And you can see it has you know, a lot of information and a lot of configuration examples that you can use. We're going to go one by one in a minute. I also wanted to show you, actually let's just get there and just go look at the configuration. So if you remember from the steps here, we need to make sure, let's just go, you know, let's just go one by one. Let's go. The first thing that we're going to have to do is just to you know, let Unbound know what interfaces are going to receive DNS queries. Right? This is what it's going to use to bind that port 53 to that particular interface. So for that, you can specify the interface command as is stated here. Still, I mean, at the end of the day, you can specify the IP address of the interface that you want, you know, the server to listen to, or you can leave it as a 0.0.0, which means every IPv4, every interface with an IPv4 address will be able to receive DNS queries. If you want to enable as well any interface with a IPv6 address, you obviously can enable interface : 0, right? But here's some examples, you know, on how to use that directive if you have to. And the next thing is that normally when you have a DNS server, you don't really want, you know, anyone from outside the, you know, you don't want to let everybody use that server, because then, you know, maybe the server is not dimensioned, is not sized to take over all the DNS queries that it can receive. So for that reason, normally it's a good practice to set an access control. And this is the way you set an access control here. The access control can be used either to allow or refuse access to your DNS server. Normally you would allow access to a server only for your local networks, right? So in that case, let's say access control column, and then we say 172.16.19.0/24 allow, right? So this is the only subnet that is going to be allowed to use this DNS server. And that way we protect the server from, you know, outsiders as well, right? Because one way to attack your server is to do a denial of service attack. So if an outsider is trying to do a denial of service attack on this server and it's not part of that network, obviously it's gonna fail, right? Okay, so that's the access control. And the next thing that I wanted to show you before we configure the forwarders is how to configure domains that are not signed for DNSSEC. And for that, let me look at it here. The directive is down here, which is domain insecure, right? So you can, and this directive here, as it's stated over there, ignores this chain of trust and it's treated as an unsecure domain, right? So you can specify the domains that you don't need to do DNSSEC validations with that directive. Domain insecure, and then you specify the domain name. In this case, we're going to assume that example.com is an unsecure domain. You know, if we have to query for it, then, you know, just don't check for DNSSEC. Right, you know, having that configured, you know, then we are ready to specify a forwarder, right? The forwarder, if you recall, is the server that we're going to forward all DNS queries to, right? If we don't specify a forwarder, what's going to happen is that this server then is going to have it's going to do a recursive query. And then, you know, one of the reasons to do that is because doing a recursive query, the server will have to go back and forth and receive data from the outside very often, and that data can tax your internet connection as well. So typically when you have a local DNS server, you can your local ISP will give you you know, its own DNS servers, and you can use, you know, the ISP's DNS servers instead of using your own server, and you can delegate the recursive query to the DNS, to the ISP DNS server. That way, you just ask the DNS question, and then you just receive the data one time, and you reduce the amount of traffic that you have on your internet connection, and you keep some of the resources. So for that, the structure is the way you see it over there, and I always like to copy it because that way I don't have to remember all of it. But these are two examples, right, on how to use how to forward it to a particular address or how to forward it to a particular host. So basically you can specify, and this is the structure. The first two lines are the same, which is a forward zone and then the name of the zone that you want to forward, example.com, in this case, example.org, right? And then next one is forward address, and this is the IP address of the server you want to forward it to, and here forward host, and then an actual DNS name. I would say that forward host is not very practical. I mean, you cannot always use it, because if your server is going to forward DNS queries, to another server, it would have to use DNS to find this host anyways, right? So it might not be very very useful if this DNS server cannot resolve the name. But obviously, this configuration that you see right here, you have the example.com zone, and then obviously that zone has an IP address, and then as you can see here, the domain for the example.org is example.com, so we'll be able to find it. But just be aware that if your server doesn't know how to find example.com, then you won't be able to forward it to a particular host. So typically, you will use an IP address, and you forward it to an IP address, right? If you want to change, if your DNS server that you're forwarding it to uses a different port, this is how you do it. You put add and then the port number. Here's the example right here. Right? For our specific configuration, what we want to do, right? We don't want to forward a specific domain. We want to forward everything. And to forward everything, let me just get rid of the we don't want to forward for a particular domain. We want to forward it for everything. So for that, what we do, the DNS zone will be dots. So that's telling the server that everything just forwarded to that particular address. And here we're going to specify the 8.8, and in case that one fails, we can specify second server. Sorry. .4.4, right? Just align it a bit just to make it look pretty. Not that it matters, but just to visually it's better. So basically, this directive is telling the server is that whenever you receive any request to any domain, just send it to this to server. And this is what you need to do to meet your RHCE objective, right? If you are being asked to create a cache-only DNS server, this is the configuration that you do. But if you have to forward traffic for a specific domain, obviously you know how to do it, right? The name, you can change it with the zone, and always use this this file to for guidance when you're doing this configuration. So we just exit out of there, and then we save it, and then we just have to restart the unbound service. All right. Now, if we try to check if the server is working, let me see the IP address of the server. IP address, all right? 172.168.7. All right. So if we check, if we ask this server for 172.16.19.7 should return something. Okay, connection timeout, no server could be reached. So let's do a check. No errors. And the service failed. So let's see why it failed. So it says error bind address already in use. So I probably have something that's still using that port 53. So let me see if I find what is it. Let's find. And then we see that there is something here, I don't even know what that is, that's using PID 1261, right? It's, so let me just kill that one. I don't know what that came on in there. Let's try to restart the DNS service. All right. Now it's running. Okay, so let's go ahead and try again. So dig at 172.16.19.7, and we're looking for www.google.com. And you know the service actually is working. So we got an A record. So even though I didn't specify the record that I wanted, since this server doesn't, it has an IPv4 address, then it defaults to an A record. But we can specify the record that we want. So let's say the quad A record that returns the IPv6 address as well. Let's get some MX records for the google.com domain. And the SOA, sorry, the DNS servers. So we got 1, 2, 3, 4 name servers, and the start of authority is obviously returning the SOA information. So the server is operational. So at this point, obviously, you should be set. Really, there is not much that you require to do to configure a caching name server. It's a very simple concept, but obviously it's important that you understand the theory, so it's easier for you to go through the configuration. So I have a proposed lab for you. So I want you to go into server 1 and configure it as a DNS caching server. Configure the server to respond only to your local network. So I include a network there, 172.16.18. But if that's not your local network, then configure it to something else, right? And then configure the server to forward all your DNS requests to 8.8.8.8 or to another server, right? So, and then the domain example.com is an unsecured domain, so make sure you exempt that domain from any DNS check, and then have a little bit of fun. Just make sure that you can that you get very familiar with this. From my point of view, for those of you that are taking the RHCE exam, this is one of those low-hanging fruits. A DNS question is very simple to get out, knock out of the park, because as you can see, there are not so many steps involved. So I hope this video was informative. Thank you for watching.